Hi everyone, and we start our section Physics Educational and Astronomical Educational on the conference of ICon-MaSTEd. We are glad to see you, and I personally we are glad to see many colleagues which I can see last year. So it's our friends from Philippines and other country, and of course from Ukraine. Okay, we start. I am Svetlana, and I with Irina was moderate this section. Irina, please can say some words.
Good afternoon, dear conference participants. I'm I'm very pleased to see among the participants from previous year, and we have today seven report. The first for article from abroad, and I think we can start. And our first report has title Conversation Factor Will Up, a tool to improve unit conversation skill in grade 20 STEM students, CNHS.
James.
And
James, turn on
James.
microphone, if you can. Okay.
I with this opportunity. So good day, everyone. I am James. I am James Quijada. So in behalf of my co-researchers, I will be presenting to you the research entitled Conversion Factor Wheel Up, a tool to improve unit conversion skills in grade 12 STEM students of Cantilan National High School. So before that, I would like to appeal to you to please bear with me because the internet connectivity in our locality is poor. But nevertheless, I will be presenting now our research. Okay. Is my report, can you see my report, everyone?
Yes, we see.
Okay, thank you so much. So again, I am James Quijada, and I will be reporting Conversion Factor Wheel, a tool to improve unit conversion skills in grade 12 STEM students. Okay, so here is the outline. We have this abstraction, introduction, objectives, methodology, results, and discussion, conclusions, recommendation, and references. Okay, so this is the abstract of our research. Now let us move on to introduction. Okay. So unit conversion is the process of expressing a quantity in one set of units as an equivalent quantity in another set, typically within the same physical dimension. It involves multiple different systems. In STEM education, mastering unit conversion is a foundational skill for STEM, particularly in STEM 12, and expressing measurements in scientific notations. Okay, please bear with me. I'm sorry because the internet.
Yeah. Okay. Yeah.
Okay, I will continue.
Okay. James have some technical problems. Okay.
Okay, ma'am. Okay, let us
Yeah,
continue.
we can see.
Did you see the screen, ma'am?
Yes, yes, yes. Thank
Okay.
you.
Okay, I will now continue. So similarly, another study found that prospective science teachers exhibit significant gaps in understanding metric unit conversions. Recent research also demonstrated that task-based interventions can enhance student skills, highlighting the potential for innovative teaching tools to address these challenges. So at Cantilan National High School, grade 12 STEM students often struggle with unit conversions involving lengths, weights, volume, and time. These challenges hinder their ability to solve real world problems that require accurate conversions. So, to address this issue, the researchers developed the conversion factor wheel, a mobile application designed to enhance a student's unit conversion competency. This tool provides an interactive and user friendly interface, making unit conversion operations more accessible and engaging. By simplifying complex operations, the app aims to improve students' understanding and performance in STEM subjects. This study seeks to evaluate the effectiveness of the conversion factor wheel in addressing unit conversion challenges faced by grade 12 STEM students at Cantilan National High School. So here are given objectives. First is to develop an application called conversion wheel. Second is to determine the effectiveness of the conversion wheel in enhancing unit conversion skills among grade 12 STEM students at Cantilan National High School. Now let us move on to the methodology. So the conversion factor wheel is a user-friendly mobile tool to aid in unit conversion tasks involving length, mass, volume, and time. The app featured an intuitive interface where students could input values and instantly receive equivalent measurements in various units. The app is especially important for Cantilan National High School students as it functions offline, providing a major advantage over other tools that require an internet connection. Now for the research design, this study utilized an experimental research design with pre-test and post-test assessments to evaluate the effectiveness of the conversion factor wheel in enhancing unit conversion skills. The design was chosen to compare students' performance before and after using the tool, enabling a systematic examination of its educational impact. The study focused on grade 12 STEM students enrolled in science and mathematics subjects involving unit conversions at Cantilan National High School. But the participants ensembling, the participants were randomly selected from two sections of grade 12 STEM students at Cantilan National High School. The total population of these students was 48, with 23 in one section and 25 in the other. A sample size of 20 students representing approximately 42% of the population was used in the study. Randomly selected was employed to ensure heterogeneity and minimize selection bias, with the students from both sections participating. So while the sample size does not constitute 50% or more of the total population, it was considered acceptable given the naturally small population size in the school. The researchers acknowledge this as a limitation and recommended further studies with larger samples to enhance the generalizability of findings. So the data collection. So to establish a baseline, a pre-test consisting of multiple choice questions and problem-solving tasks and unit conversions was administered. After the intervention period during which the conversion factor wheel was utilized, an identical post-test was administered to measure improvement. Additionally, a questionnaire was distributed to collect qualitative data on students' experiences with the tool, focusing on usability, satisfaction, and cognitive load. Now let us move on to data analysis. Quantitative data from the pre-test and post-test were analyzed using statistical measurements, including the mean, the standard deviation, paired t-test to assess the significance of score improvements. The significance level was set at P0.05. Qualitative data from these questionnaires were analyzed using thematic analysis to identify common themes related to the tool's usability and effectiveness. The use of both quantitative and qualitative data strengthened the study's validity and provided a comprehensive evaluation on the conversion factor wheel's impact. By incorporating random sampling, acknowledging the constraints of population size, and combining both quantitative and qualitative analysis, this methodology ensures a robust evaluation of the conversion factor wheel despite the limited sample size. Now let us move on to results and discussion. So Table 1 presents the post-test scores with proficiency levels, the pre-test and post-test scores with the proficiency levels of students using conversion factor wheel. So we have students from 1 to 20, and they have the highest possible scores, which is 10. And now let us have the results from pre-test and post-test. First, we have from the pre-test, we have the mean score from the actual score that is 4.8. The percentage is 48%, and the proficiency level is not proficient. However, in the post-test, the mean score is 9.45, the percentage is 94.5%, and the proficiency level is highly proficient based on the legend given. Now let us move on to the table 2, the descriptive statistics of pre-test and post-test scores. So the pre-test and post-test scores, the mean is 4.650, and the standard deviation of 0.587, the standard error 0.131, the 95% confidence interval, the interval of difference is 4.925 to 4.375. The t-value is 35.418, and DF is 19. So table 3, paired t-test results comparing pre-test and post-test scores and its statistical significance. So the mean difference of pre-test and post-test scores is 4.650. The t-value is 35.418. The decision is rejected, and the interpretation is significant. Now let us move on to the table 4, the student's psychological validity of the conversion factor wheel. So we have the different questions given. The questionnaire 1, perceived usefulness. Questionnaire 2, perceived ease of use. Questionnaire number 3, satisfaction. Questionnaire number 4, engagement. And questionnaire number 5, cognitive load. So the mean score of these questionnaires, or the question given, are 74.13%. And having this, the weighted mean of 3.70, and the verbal description that is good. Okay, now for table 5, the interpretation of sum up data and psychological validity. So we have the psychological validity questionnaires from questionnaires 1 to 5, that is the same result as given to table 4. Okay, now let us move on to conclusion. This study demonstrated that the conversion wheel is an effective instructional tool for enhancing unit conversion skills among grade 12 STEM students at Cantilan National High School. The significant increase in post-test scores, coupled with the students' high satisfaction rating of 74.13%, underscores the tool's positive impact on student learning. The findings suggest that the conversion wheel not only provided improved students' performance, but also addressed their challenges in mastering unit conversions, making it valuable resource for STEM education. Now for the recommendation, it is recommended to examine its long-term effects on on students' academic performance to assess its sustained impact, compare it to traditional methods and other digital methods existing, integrate the conversion wheel into teacher training programs, and national STEM curriculum guidelines is recommended to promote innovative instructional practices and identify any problems associated with the app. So these are references. Okay. So thank you so much for listening, everyone. That ends my talk.
Okay, thank you, James. It's a very interesting and useful apps for students of physics which study physics in the secondary and high school. Okay, colleagues, any questions? Okay.
Dear participants, we invite you to discuss the report.
Okay, Sergey Alexeyevich, you want to ask? Okay, please.
Thank you, Svetlana. Thank you, James. I have two questions. In your methodology sections, you indicated that you use a mixed methods approach. But in your report, we have seen, first of all, quantitative data. My first question, what about qualitative part of your research? What think the teachers and your students about using conversation wheel app?
Pardon, sir. Can you repeat the question, please?
Your methodology part have a mixed method research as declared. In your talk, you presented, first of all, data quantitative. What about qualitative part? Some message from teachers, students about using the related application.
Yes, we have this qualitative data. I guess the qualitative data, it is all about the psychological validity on the students, especially on the usability of the app. The students use the app, and then we have employed this pre-test and post-test. So in pre-test, it is to measure the initial knowledge of the students without using the app, and then we employ them in a regular classes. Then we took another test that is a post-test to measure their improvement. Then at the same time, while we are having the post-test, we are also giving them show the satisfaction rating based on their psychological validity, and it based on the result there is 74.13 rating. So I wasn't able to present it thoroughly because due to time constraints. So like for example, I have present like for example the perceived usefulness. There are various questions. There are different questions under the perceived usefulness, the perceived ease of use, the satisfaction rating. So there are a lot of questions that would fall under the qualitative data, especially with the experiences of the students and the teachers as well.
Thank you, James. That you don't use any focus group discussion or interviews. And my second question related to the scalability of your experience. Your experiment was related to one school, but your applications developed, I think, in English. So it can be used in the, more school, in other educational setting, etc. Do you indicate in your paper the link to download your application, or it available in Google Apps or another stores?
Okay, thank you so much. So with you are referring to the application is not only it's not only solely for a certain school. So I believe this application it can be integrated at various schools, since a lot of students can relate with it. And on the other hand, this application is more advantageous for students because it can be utilized offline, meaning that it doesn't need internet connectivity, and they're able to convert the units and measurements, so even in offline. So your another question is that um, the 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 application is still ongoing, so we're still improving the application. It's still not yet on the App Store, so we are still because we are researchers at the same time, we make sure that it is uh, we present a high quality. It's not just about once we have developed a certain app and then we let it let the people use in our part, in our end, there still need an improvement before it can be downloaded by a link or in certain app store. So we're still working on that. We're still improving for this application to be utilized and to be used by the students for them to improve their academic or for their academic progress. And of course, that is really important to enhance the learning outcomes and support students' academic progress. Yes.
Thank you so much both for your talk and answer. But I think there are many another questions to your talk. So my silence.
Thank you, sir.
Okay,
I
Irina, you
have a
have?
question too. Do you plan to add more STEM topics to your app in the future or
Ma'am,
not?
pardon?
Do you
Repeat.
plan to add more STEM topics to your app in the future?
That is something. Yes, ma'am. Thank you so much. So that is something that we're looking forward and we're working on together with my co-researchers and to the professors we have and my co-researchers. We're looking forward to improve the utilization of this unit, the conversion factor wheel, especially that it integrate with the students. So we are planning to make it more uh, we need it to improve, and that is why this is really necessary, because this study is not just about the app, but it's all about looking forward for bringing academic success in the students. So this app is an innovative teaching tool that significantly improve the students understanding of the unit conversion. So we are looking forward for that, ma'am, and we are working on that with my co-researchers.
Thank you for your answer.
Thank you, ma'am.
Okay. Thank you. I have some small question because do you have any feedback in the app? Can you change or correct who is a student, which student using and or result of the students?
Ma'am, if there are in a result, what can you repeat the question,
Can
please?
you change result of your student with this app, with this wheel? Or
The
result can see only students themselves.
So we are looking forward. The main purpose of this app is to help the students, especially not all students, or especially in the STEM students, or not all STEM students, or not all students are able to convert the converting units from length, mass, volume, and time. So what we have given in this app is that it's a fixed result that could give there's a fixed result or fixed answer whenever they try to convert those length or unit. So the main purpose of the app is to help students, especially those who are unable or they find it difficult to convert the unit of measurement.
Okay,
Yes,
I
ma'am.
understand. This app's not for environment, but it's only helping for students. Okay, thank you.
Thank you, ma'am.
Thank you. Are there any questions? Okay, thank you, James.
Thanks.
And next presentation from Frank Angelo Pacala. Smartphone simulated and science learning, rethinking physics and experiments. Okay, thank you. Frank, you can. Frank, turn on microphone maybe.
Hi, good afternoon to
Okay, thank you.
can you see my screen? Is it on?
Yeah, we can see.
Thank you.
All right.
Thank you for the affirmation. I can see similar faces from the last year. Miss Irina, Mr. George, who else? Siltlana. So, Здравствуйте, привет, как дела? Нормально? So I hope you are.
Thank you for your.
I hope you're doing
All right.
well in Ukraine right now. So while I am here in my room in Uzbekistan, where I am teaching. So this output is of myself. Also Sergey. Hello, Sir Sergey. Nice to see you again in this conference. So this project is of mine and my wife. So we are the authors of this smartphone simulations and science learning, rethinking physics experiments. So oftenly, students associate science with hands-on lab equipment. So what you can see in the picture are output coming from my class. So I'm teaching grade 11 students. So normally we are using traditional equipment, but they don't look like traditional in a normal class actually. They look like sophisticated, but on the left side of the picture is a traditional apparatus in thermal physics. And then on the right side is a modern data logging apparatus in the topic for conservation of momentum. As I said, there is a limited access to traditional science tools, and it is actually a global issue, especially in countries that belong to the global south. Countries that are experiencing, for example, war, experiencing poverty. So usually they don't have access to this modern equipment. So emerging technologies such as smartphone experiments, online simulations, they offer flexible, low-cost alternatives. So these tools promote independent exploration, student engagement, and data-driven learning. So this study explored how students experience and perceive these tools over a school year. So mostly in my classes, I use conventional science equipment, and on top of that, I'm also using PhET simulations and smartphone application. For example, in the picture that you see on the screen, so there we are measuring the magnetic flux density of a solenoid using an application called PhET. So using this series of experiments for a whole school year, we would like to know the experiences, the lived experiences, and the perception of students towards these tools. So the research questions are, how do smartphones and PhET help conduct physics experiments more effectively? How do smartphone-based experiments features improve the learning experience? How comparable is experience to traditional hands-on experiments to simulations and smartphone-based experiments? And what challenges are evident when using smartphone for physics experiments? So these are my research aims and questions. So this study is underpinned by the model called Technology Acceptance Model, or TAM. So the TAM explains behavioral intentions in using technology, like perceived usefulness, perceived ease of use, attitude toward the technology. So these are the three constructs that are attributed to the TAM and then to simulations and smartphone-based experiments. So what does the literature says? So there are a lot of quantitative studies about smartphones and PhET. So if you will go to Google Scholar and write the keywords smartphone-based experiments and PhET simulations, you will be bombarded with a lot of these studies, and mostly are quantitative, like Hochberg et al. 2018, Yunzal and Casinillo 2020. So according to Chai et al. In 2020, they suggested that more qualitative studies in these fields are needed to better understand the relationship of various constructs like conceptual understanding, engagement, perceptions, and the like. So in this study, because of ethical considerations, so I have actually grade 9, grade 8, and grade 11 students, and this is a total of nearly 100. But because of ethical considerations to follow, I only have 8 students in this case study. So since there are only 8 participants, according to Bascarada 2014, so case study is more appropriate. So the framework of Bascarada 2014 is used: preparation, collection, analysis, and sharing. So for the preparation, the students underwent several training and studies in physics using smartphone-based experiments and online simulations. So during the interview, before the interview, an informed consent form was given to the parents, and of nearly 100 informed consent form, only 8 reached me. So that's why I only have 8 participants. So this in a qualitative study that is involving minors, it's really a hindrance to data collection, to sampling, is the ethics. But what can we do? That is our life as a researcher. We need to follow ethics. So during the collection, so individual semi-structured interview was done using a smartphone. So the smartphone used as a recording device, and then the transcription was done using the MacBook. So the MacBook has a application that can transcribe voice into text. So then when the transcriptions were done, and I have the text, the narrative text, structural analysis of the various narratives to generate themes was conducted. And then when I generated the themes, hermeneutic interpretation was conducted, and also iterative process. Now during the sharing, I conducted a focus group discussion with the parents and then the participants to share the result and to confirm if these are the themes that they really have experienced, or there is something that must be added or removed from the report. So far, there was no things that were added nor removed, and the participants confirmed their the transcripts and the themes. So these are the key findings. So the main theme 1 were about affordances of smartphone-based experiments and online simulations. According to the participants, there were 4 affordances. First, increased student engagement, connection to reality, practicability and accessibility of learning, and enhance conceptual understanding. So if we are if we are STEM teachers or engineering teachers, usually we deal with theory and then we deal with practical applications. So when we only deal with theory, we cannot connect to reality. For example, Planck's constant. The students will just know about Planck's constant or the value of the constant, but they do not know how is this used practically in a lesson, or let's say acceleration due to gravity. What is the importance of these values and how we can find out these values in a real terms. So these were the connections to reality. So since the smartphone, as I said, not all schools will have laboratory apparatuses. So the smartphones are there, and I know almost all students, individual students, have individual smartphones. So not only that, on top of that, that means each student's smartphone is a moving laboratory, right? It's a laboratory in itself, by which the students can carry several experiments in physics. Well, maybe there are applications also that are pertaining to biology or chemistry, but I don't know because as far as my understanding is concerned, I am only related to physics. So that is about theme 1, affordances. So theme 2 is about enhancing the complementing role of digital tools to the traditional hands-on experiment. If we look back at the picture here, so there are two stories here. The first story is about using conventional and traditional laboratory apparatuses. For example, high-low voltage generator. You have the multimeter, the connection wires, and the solenoid. But now, these conventional apparatuses are now complemented by a smartphone. As you can see in the picture, the smartphone now is used to measure magnetic flux density. In our lessons, magnetic flux density is a very difficult concept, and it's difficult for the students to comprehend this, for example, measuring this, how are these found, and all of those things. So if we will not conceive a plan, a lesson plan, in order for the students to fully grasp and understand this by using a smartphone per se, for example, so then we will put our student at bay, and they will not get the clear competency or standard that actually the curriculum intends the students to get. So more so, there are also challenges that were reported by the case study. So the challenges are cognitive challenges, technical limitations, equity issues, and challenges in accurate data collection. So for example, in cognitive challenges, the students may not know if they are not, for example, versatile, or they are not fully grasped with the how to align these things, how to set these things. So they might have a challenge with that. And that covers also the technical limitation. So in terms of equity issues, the students realize that how about for the students who are not having smartphones and whose schools do not have proper laboratory apparatuses. So the education is not equal, correct? And they are mostly left behind in terms of the educational process. So that's why education is not actually equitable for all, and I hope there are we focus more of our money to education than focusing to for example, to wars and everything of that actually doesn't matter in the world, while educating our children for the progress of the future is most important. So also there's a challenges about accuracy in data collection. So as I said, if the students have technical limitations, they might not get the correct data because there are technical aspect of the application that must be set. For example, the decibel of the audio of the application must be set. set, the tone, the magnetic flux ability, and all of those things. So the results align with the technology acceptance model, which emphasizes perceived usefulness, ease of use as factors influencing the adoption of the new technologies. So the complementary role of the traditional and digital methods supports Furious et al. 2015 observation and Brinson's 2015 comparison of physical and virtual experimentation. Also, Chu et al. 2023 and Al-Marashdi and Saleh also highlight the positive perception of digital tools and proper training significantly influence student engagement and learning effectiveness. So what are the surprising findings and insights from our paper? So firstly, an unexpected insight was that the students have a nuanced understanding that the digital tools are not meant to replace traditional methods, but they are rather to enrich and complement them, just like my example a while ago. Equally notable was their awareness of equity issues. So now, it now becomes an interdisciplinary issue because, as I said, not all children will have smartphone. Now the global perspective comes into place. How will the teacher moderate that perception coming from the students is very important. Now, students also demonstrated critical thinking about data accuracy, recognizing how environmental noise, for example, device instability can impact results. So, in conclusion, three major themes emerges. For example, the affordances of smartphone based on online simulated experiments, complementary role of the digital tools, the challenges in use, and the implication is that teacher training is crucial. So, and students training as well. If the students doesn't know how to manipulate the smartphone, that means the teacher also doesn't know. So teachers and students must be trained as well. Of course, according to OECD in their report prior to the PISA, they revealed that smartphones are hindrance to learning, especially in OECD countries. So that means we must have a comprehensive smartphone use policies. For example, in our school, we need to write a letter to the principal before we can use a smartphones. We have a very strict and extensive smartphone policy use in our school. And also, broader studies are needed because the limitation, as I said, of the ethics, as far as the ethics is concerned, we ended up having only 8 participants, but I don't know in the near future, maybe experimenters, researchers can have more than 8 experiments and can have grounded study in relation to these things. So I think I have consumed a lot of time, and thank you so much for listening, and have yourself a great day there wherever you are, and God bless us all.
Thank you, Frank. Today's when we haven't modern equipment, we haven't modern physics class, smartphone is really useful. And it was used in the class, in the schools, in the high school, and in the science research. So I have a small question. What do you think? On all the terms from physics, we can use a smartphone for a practical task, or there are some practical tasks where we can't use today's smartphone.
The next experiment I was trying to solve is to measure the speed of light using the smartphone. If I can do that, then I would really be happy, and I will publish that article measuring the speed of light using a smartphone. But I am trying ways how to do that, and unfortunately, Miss Siltlana, not all experiments can be made by the smartphone because the smartphone itself has limitations as well. As the theme said, technical limitations. But it's better than nothing, right?
Yes, yes. Yeah, maybe because I'm think so. Uh, I can't use smartphone of the molecular physics or measure pleasure or some no, some useful mentioned on the physics. Okay, thank you. Other questions? Yeah, colleagues, you can uh, ask your question in the chat. Okay, Irina, please.
In your report and your presentation, we can see what do you think about your study, your student. But what do you think about your study and how evaluate your study to expert about which you write about them on the slide?
Yeah, we don't, as ethics, we don't write our students on the slide or in the report.
No. You write about two experts on this slide.
Yeah. I'm sorry. I have not. I wasn't able to mention that, but yeah, two experts. They validated the themes that resulted. So that's their utilization in the report. So they validated the transcripts, the themes, if they align really to what I have written.
Okay, thanks.
You're welcome, ma'am.
Okay, thanks for your question and for your answer. Are there any questions? Okay, thank you, Frank. And as for me, next report was very interesting because it is from our colleagues George Columbus and thematics fostering early understanding on vaporization in 5-6 years old with engineering design. So we
I think that not George, but Georgi.
okay, Georgi, yes.
It's a cradle of civilization. It's a beginning of our Ukraine. Crimea, Tavria, it's all of us. Thank you, Georgi.
Okay,
Hello
I'm
to
sorry.
everyone. Hello to everyone. Yes, I totally agree, Dr. Semerikov, and I am happy. We are happy as a team that we participate this year too in this great conference. And I am also happy that I can see people that we have met last year, as Frank, as Mr. Frank told before, Mrs. Irina, Mrs. people that we are together this year too. I will the PowerPoint. Just a minute.
Okay.
Okay, can you
So-
just tell me that you can see the PowerPoint? You
Yes, we
can?
can
Yes.
see.
Yeah, okay. So I will start. So today I will present you a study that we have done with a PhD student, Michalis Ioannou. Myself, I am George Kalliambos. I am an assistant professor in the University of Patras in Greece, and assistant professor Panagiotis Pandidos, who is working in the University of Athens, a national and Capodistria University of Athens, and of course, Professor Kostas Ravanis, who is in the University of Patras too. So the title is, as you told before, Fostering Early Understanding of Vaporization in 5 to 6 years old via Engineering Design. I will explain you what is it. But before, as last year, I will present some slides about my country, and of course, Ukraine and Greece, we are in a distance of around 1,400 kilometers, as I see in Google, but historical and cultural links bond the participate in a way in this bondage too. So last years I have shown you some photos of my city, which is Patras. This year I have brought some new ones. So in Patras each year on around February takes part a carnival, Patras Carnival. Of course, you can see a photo here. Of course, it is not so big like Venice or Rio de Janeiro, but we are proud that many people of citizens of Patras participate in this carnival. You can see a local winery where you are welcome.
I'm sorry, George. We have some technical issue. We see only your title slides, but not see another slides.
Really?
Probably. Oh, can you share your full screen so we see your presentation in slides mode?
Yes, thank you. I don't know why this happened. I will try it again, and you will tell me whether you can see
Excellent,
it.
excellent. Oh, Patras C. Yes.
Okay, and here it is, as I told you. Okay, now you could you tell me if you can see now the slide which shows Ukraine and Greece? Okay, okay.
Yes,
So
yes.
here, okay. So as I told about the bonding. So now here is the photos of Patras. So this is the Patras Carnival. This is a local winery where you are utmost welcome if you ever come to Greece and to Patras to try our local wine. And of course, the beaches of Greece is always been welcome for you. And Kalogria Beach is a beach near my home city, Patras. And here you can see the university, our department, and my office. Here is George's office where I am speaking from you now. Okay, so now I will start my academic presentation. So as I told you before, we are a team where we try to search, to study science education for early constructive in theory is a theory of this theory lies mental representations, which are ideas that the children hold. Their origins come from natural world, as you can see, for example, a tile is colder than a wooden table, and from socio-cultural world, for example, expressions like close the door so the cold doesn't get in can make can cause a lot of alternative ideas in students. Nevertheless, within early childhood science education, there are some precursor models, which are cognitive entities, and I will now try to explain you what is these precursor models. So they are models that interpose themselves between the original children's representations and the scientific models used in education. So they are something, they lie between what is scientifically accepted and what is alternative ideas of students. And the idea is that because we are talking about extremely young children, what we need to do is to help them to get the precursor models, and after some years, they will transfer from the precursor models to the scientific acceptable models. This is their idea. So we did an experimental investigation. It was qualitative in nature, and we split the study in three parts. There was a pre-test, a teaching intervention, which we call engineering design process. I will explain you in a moment what it is, and then post-test in order in children aged 5 to 6 years old, 9 boys and 10 girls. And the study aims to answer the following research questions. To what extent children mental representations about vaporization could be transformed through a structured teaching process, this is engineering design process, leading to the construction of a precursor model. So, regarding the pre-test and post-test questions, I will read them for you. We ask them, do you know what steam is? Have you ever heard the word evaporation? Have you heard the word boiling? Have you ever gotten your clothes wet? What did you do then? We ask the children if we put a glass of water in the yard under the sun, what would happen to it after a while? We told them that the sea is exposed to the sun every day. What happens then? In order to talk to us about evaporation, and what will happen if we boil water. These were the questions in the pre-test and post-test. And in the middle, we formed the engineering design process. So this process is aparted from 4 stages. The first stage is the problem stage, where a story was presented to children, introducing to them 2 problematic situations. In the inquiry stage, where children proposed solutions to the problematic situations. Designing and testing stage, where children desired, with the help of the teachers and the researchers, their proposed solutions. And then the conclusions and presentation stage, where students had to create a poster that addressed the problematic situation. So, regarding the engineering design process and the 4 stages. In the first stage, we give students the following story. I will read it to you. Literally, it is a name of a child, lives in a village near the sea. While playing, a wave suddenly shocked him. His shirt was wet. What will Argyris do now? The second one was Argyris was sitting on his balcony on a sunny day, filling a glass of water to drink. Suddenly, Irene, a girl, called him to play, and he left without drinking the water. When he returned, the glass still seemed strange. Why? Then, in the inquiry stage, children made predictions and proposed solutions, trying to understand where the water goes when clothes dry, and what happens to the water in a glass if a glass left outside. In the designing and testing stage, the following experimental situations took place. The first was soaking a piece of clothing and hanging it to dry inside the classroom, while the children was observing them at intervals. Moreover, placing a glass of water outdoors in the school yard in a sunny spot, having it at intervals. And finally, heating and boiling water using a portable burner. Then, in the final part of the engineering design process, conclusions in the conclusion and presentation stage, students had to create a poster in order to address the above mentioned problematic situations. Here is a table with results. I know that there are a lot of numbers on it, so I will continue with some indicative results. So regarding the pre-test and the post-test, I have just picked some of the questions. So, for example, in the question 2, have you heard the word evaporation before? What it is? The responses was allocated in sufficient responses where children describe the phenomenon of evaporation, mentioning factors such as heat source and water. For example, students told us it turns into smoke, the water, from the sun because the sun is very hot and can make it smoke. In the intermediate responses was allocated those where children described their experience without with evaporation, and focusing on the outcome without mentioning the conditions for evaporation, such as heat. So, for example, it drive evaporation. When you start the engine and step on the gas, the exhaust emits smoke. You can see question 3. Have you heard the word boiling before? I will read you the sufficient response. For example, it produces bubbles and the water heats up. The intermediate response, it boils in the pot, it gets hotter, and an insufficient, for example, the water melts. And finally, question 6, the sea is exposed to the sun every day. What happens then? A sufficient response is the following. The sun just sees and it evaporates. When we wash our hands, it goes back and forms a cycle. Here you can see that the child referred to the water cycle. And in the immediate response, for example, some water goes to the sky, but the child did not mention anything about evaporation, and an insufficient response, it heats up in depths because it has holes. Now, regarding the engineering, the EDP process, in the problem stage, we get some drawings from the children. So here you can see, for example, how Argyris clothes will dry. And as you can see in the drawing, there is a clear reference to heating from the sun and the air. You can see here the sun and here the air. In the inquiry stage, we developed a concept map depicting children's ideas of the actions Argyris should take to dry his clothes. For example, to shake the water off, to run, to use a hair dryer, to dry with a towel, or to be in the sun, smoke, and finally, evaporation. In the designing and testing, for example, in the experiment, hanging a wet shirt to dry, you can see the researcher asked, what will happen now? It will dry. Where will it dry faster? In the sun, says both children. Has the water in the shirt decreased? Where did it go? It go into the air. It dried. So these are scientifically accepted responses. And finally, in the conclusion and presentation, you can see one poster of a group of children. The children were into pairs, working into pairs, a poster that addresses the problematic situation with the sun, the heat source, and the water, and how it goes out of the shirt. So, in the pre-test, only 10% of children attributed meaning to the terms vapor, evaporation, and boiling, while after our teaching intervention in the post-test, answers compatible with school scientific knowledge range from 26 to 9%. And a qualitative aspect, children consistently attributed a thermal character to the phenomenon they described. So they started to connect evaporation with a heat source. And regarding questions 4 to 7, in the pre-test, answers compatible with school scientific knowledge range from 0 to 37%, while in the post-tense, this percentage is changed to range from 16 to 100% in some cases. So the data provides strong evidence that children are capable of constructing a precursor model regarding the issue of vaporization. Within this precursor model, children can make descriptions and predictions based on thermal exchanges. This was our goal. And the engineering design process seems to play a key role in facilitating such a model formation. Of course, there are some study limitations. For example, we acknowledge that our sample was small, and moreover, it was a convenient sample drawn exclusively from one kindergarten class. For further research on vaporization through quantitative approach, through a larger sample, and through longitudinal approach, so that we can get to these children after, let's say, 6 months to see what they will respond in another post-test. So thank you very much. Here is an indicative reference, and thank you again for listening to me.
Thank you, Georg. I think so that physics children must study from the early, but it's very difficult, really difficult, because they don't know some definition, some material. And my question, small, for beginning, how the material modified to make concept of understanding at this age? How many words and material of physics you used? Or
Okay. First of all, thank you for the question, and I totally
and
agree with you
if you listen.
Yes, I listen to you, and okay. First of all, thank you for the question, and I totally agree with you that it is a fact that in early childhood education, teaching physics is quite difficult, and this is why we have turned to precursor models, so that we can we do not try to give children the totally scientific acceptable idea, but something less. Now, regarding the material, we did some experiments, as I told before, so that we boiled water, we put water in a shirt, and we left it outside. So we tried with everyday materials to see what happens. Our main goal was to make children to manage to make a connection between thermal exchanges and vaporization.
Okay, thank you. So,
Thank you too.
okay, and dear colleagues, please. Oh, okay, Irina.
Maybe me. I remember that last year you had similar topics.
Freezing and melting.
Yes.
Yeah.
And my questions. Where do you look for inspiration? And next, now educational content is very popular. Have do you ever thought about adapting your ideas into a cartoon or any formats?
Okay, I will answer in both questions. Thank you very much too for the question. So regarding the first question, as I told in the beginning, this is a study of a PhD student called Michalis Ioannou. I am the one who is presenting it, but the work is more to him. He is a PhD candidate, and he is this kind of stuff. This is why we presented last year a part of his ongoing PhD, and this year we decided to present to you a similar thing. That is, all this is under a PhD degree. Okay? Did you understand me? Yeah. Okay.
Yes.
Regarding the second one, yes. Regarding the second one, it is a fact that we have not think about it, but it is a good idea, and we may
I want to see. I want to see a cartoon for very for physics. Simply word.
Okay, okay. Thank you. Thank you. Thank you.
Yes, thank you very much. We experimented with not preschool children, early grades, with 4 panel comic in some concepts of biology, and
Okay. Okay, good.
our children see comic in any type, and a kind of scientific comic. Moreover, with well-known heroes, Spider-Man we used, etc. So it's can be a good approach. I'm very happy that you really used constructivist theory, moreover social constructivist, so it's our links connections is Vygotskian theory, and along
Yeah,
with
of course.
it's for early grade and preschool education. It's an excellent. Thank you very
Yeah.
much.
Thank you very much too. Okay.
Okay, maybe another question. No question. Then we can go to the next report, and this is information, educational environment, and scientific process skill, experimental evaluation using the Likert scale. Author Aygerim Abdullayeva.
Good day, esteemed participants of this conference. Can you hear me well?
Yes, we hear.
Okay.
Yes.
Okay. I am deeply grateful for the opportunity to share with you the result of my research endeavors on the topic of information, educational environment, and scientific process skills, experimental evaluation using the Likert scale. My name is Aygerim Abdullayeva. Modern information educational environment is an integral part of the digital transformation of education, which is based on information and communication technologies. The information educational environment is an integrated system of digital tools, educational resources, and organizational conditions that provide interaction between students and teachers, access to learning materials, and support for individual educational trajectories. As Seymour Paper, pioneering figure in educational technology, once stated, the introduction of technology into education is not a mere addition of tool, it is a fundamental change in the process of learning. These perspectives urge us to move beyond superficial adoption of digital tools and instead examine how these tools reshape the very nature of teaching and learning. In this context, the integration of the information educational environment should not be viewed merely as a technical upgrade, but as a transformative pedagogical phenomenon. It redefines the roles of both teacher and the learner, shift the focus from transmissions of knowledge to the co-construction of meaning, and opens up new avenue for differentiation and interactivity and inquiry-based learning. This leads us to a central question that underpins our research. What is the pedagogical potential of the information educational environment, and in what ways can its capabilities be effectively utilized to support and enhance the learning process? To address this question, we examined how the information educational environment can contribute to the development of students' experimental and research skills, particularly in the context of science education. And this study aimed to evaluate the pedagogical potential of information and communication technologies in enhancing students' scientific process skills through a systematic approach to integrating ICT into physics laboratory work. Drawing on the insights gained, we developed a step-by-step pedagogical model for the structured integration of ICT into physics laboratory activities. This model included 3 key components. First, the selection of ICT tools, the design of laboratory tasks that aimed at ICT-based activities to foster core scientific process skills, including hypothesis formulation, data collection and analysis, and evidence-based reasoning, and the gradual implementation of the model over a 3-year period, allowing for a systematic and sustainable transition of ICT-enhanced laboratory practices. In our national curriculum, physics is introduced as a formal subject beginning in the 7th grade. Recognize the growing role of digital technologies in education. We conducted an analysis of computer science curriculum for grades 7 through 9. Our aim was to determine the extent to which students acquire skills relevant to the use of resources within the information educational environment, and how these skills might be effectively integrated into the learning of physics, particularly in the context of laboratory activities. The analysis focused on the content of computer science chapters and their alignment with opportunities for cross-curricular integration. We examined both spreadsheet and programming competencies with particular attention to their pedagogical relevance in experimental physics. And the findings are summarized in the following table, which you can see on the slide. This analysis demonstrates that students possess foundational digital skills acquired through the computer science curriculum that can be purposefully transferred to the study of physics. Building on the interdisciplinary potential of computer science and physics, one of the key principles guiding this study was a gradual, developmentally appropriate integration of ICT tools into laboratory-based learning. To ensure pedagogical effectiveness and cognitive alignment with students' abilities, we structured the progression around a 3-stage model: adaptation, development, and self-realization, each corresponding to a specific phase in students' academic and psychological growth from 7th to 9th grade. The adaptation stage in 7th grade, students were introduced to foundational digital tools, primarily through the use of Excel. They learned to enter experimental data into spreadsheets, apply simple formulas, and organize information in tabular form. And the development stage corresponding to 8th grade involved a shift toward more independent engagement. Students began to handle more complex experimental data, analyzing results using spreadsheet functions, and interpreting trends through graphs. Finally, in the self-realization stage, 9th grade, students demonstrate the capacity to work autonomously and creatively. They engaged in computer modeling of physical phenomena, developed simulation using programming tools such as Python, and integrated database for managing and analyzing the large sets of experimental results. To empirically assess the impact of ICT integration on students' scientific process skills, the study was conducted with 56 middle school students aged 12 to 15, divided into 2 groups: an experimental group of 27 students and a control group of 29 students. The experimental group participated in ICT-enhanced laboratory activities that incorporated spreadsheets, sensors, and programming tools, while the control group followed a traditional laboratory format that relied on printed instructions, manual measurements, and paper-based data recording. To measure the outcomes, we developed a customized self-evaluation questionnaire based on the Likert scale designed to capture students' self-perceived proficiency in a range of scientific skills. And the instrument included 31 items covering 9 core skill domains, which you can see on the slide. And students rated their agreement with statements related to these competencies on a 5-point scale ranging from 1 absolutely disagree and 5 totally agree. Quantitative results from the self-evaluation questionnaire revealed improvements in all 9 skill domains among students in the experimental group following the experimental training. Table 1 summarized average pre-test and post-test scores for each domain, highlighting notable growth in the scientific participants. Statistical analysis of the answers to each question of the questionnaire showed that the average amount of points received for answering the question I can identify the contradiction underlying the research problem, or I can formulate the research problem in accordance with the highlighted contradiction is minimal. This demonstrates the low ability of students to formulate a research hypothesis independently. The results of the study show that their students' skills to independently plan experiments and draw conclusions on the work are less developed, but their skills to select equipment and software, use a spreadsheet to build an analysis graphs are at a higher level. This study provides compelling evidence that the thoughtful and gradual integration of ICT into a physics laboratory environment significantly enhance the development of students' scientific process skills. The approach was grounded in a 3-stage model: adaptation, development, and self-realization, which guided the first introduction of digital tools in a manner aligned with students' cognitive and motivational development. Starting with basic skills such as data entry and formal application in Excel, students evolved toward complex tasks such as data analysis and digital modeling of physical phenomena. This systematic progression not only deepened students' technical proficiency, but also cultivated their capacity for independent inquiry, critical evaluation, and creative problem solving. And I'm almost at the end of my presentation. To summarize the key points, information educational environment thus emerged as both a technological and pedagogical space that supports student-centered inquiry-based learning. The evidence from the pedagogical experiment confirms the effectiveness of the proposed model in fostering not only specific scientific skills, but also broader competencies related to collaboration, self-assessment, and digital literacy. And these findings point to the need for further development of methodological frameworks and instructional resources that support the sustained use of ICT in science education. Expanding this model to other subject areas and educational levels would strengthen its relevance and contribute to a more integrated and research-oriented approach to teaching in the information age. And the future work may also explore how teachers can be supported in mastering these tools and strategies to ensure that all students have equitable access to high-quality, digitally enriched science learning. Thank you for your attention. If you have any question, I am ready to answer.
Thank you, ICon-MaSTEd. Maybe someone has a question.
Are there any questions?
I have a question.
Okay, Irina.
What specific physics experiments worked best with this ICT integration approach?
Mechanics experiments, because in Excel we must analyze the data of mechanical experiments
Okay.
And our experiment is carried at a school the experiment was conducted at a school in the Jiu-Jitsu region, grade 7 to 9, and the main topic at these grades is the mechanics. So we conduct the mechanics experiments.
Okay, thanks.
Okay, thank you. Yes. Okay, Olena Trifonova, you have a question, please. You can ask. Or microphone turn on.
Thank you. Can I ask you how many points of Likert scale did you use? And what are the names of labels?
5-point scale of Likert scale I use, and totally disagree and totally agree. Is a main point of Likert scale. And the evaluation of scientific process skills was carried out according to specific criteria I had previously developed. So these criteria are not detailed in this present study. Nonetheless, assessment results are included here and show consistency with the students' self-assessed levels.
Thank you so much.
Okay.
Thank you. Thank you. Are there any questions? Okay, maybe
a small remark, not a question. Dear colleagues, I'm really happy that we have today an exciting romance with social culture and theory. For example, I see both its foundation, I see the showing of paper, etc. In our new journal, Science Education Quarterly, which I try to share in the chat, we starting the publication of, no, I'm sorry, it's a postmortem book of my dear teacher and friend, Ilya Alexandrovich Teplitsky. And in this book was inspiration, constructivist theory. His PhD was related to different application of constructivist theory in physics and computer science education. So in the next issue of our journal, I happy to present two studies from this book. The first related the introduction, the computer and mathematical modeling using spreadsheet, Excel, and others to 6, 7 grade students, even can be 5 grade students. Not a physical, but a really science model. How can we share some talks between us about what will be tomorrow, what will be what we hear about it in Ukrainian, it's a модель поширення чуток. And the next studies will be related the computer modeling in physics and again in spreadsheet. Despite the journal is quarterly, we prepare and all these studies will be published in journal Early Access. So even due to the title 12 studies studies on computer modeling, we will have also a certain study related to using neural network modeling in science education. It's factically the last last will of Ilya Alexandrovich, so I will be happy to present it to our big community. Its publication will be in English only. Thank you. I'm sorry for...
Thank you, Sergey, for useful information. Okay. Okay, and we starting next presenting case. Okay, from company of Ukraine. It's Олена Трифонова, Микола Садовий, Ольга Речина, Наталя Донець, computer modeling of atomic molecular states, loading of Maxwell distribution. Okay, thank you. Natalia, I'm sorry, Natalia, Olena was.
You listen me? Good day. Good day.
Yes, yes. Thank you,
Can you see
microphone.
our
Okay.
presentation? See?
At least the title slide.
Yes. If I.
No.
Oh,
Okay,
yes,
yes,
strategy.
next.
Yes, sir.
Yes. Our presentation, our research, computer modeling of atomic molecular states leading to Maxwell distribution by co-authored Микола Садовий, Олена Резіна, Ольга Резіна, Олена Трифонова, Наталія Донець. The purpose of the article to investigate the problem of transition of students' learning from the educational model on information accumulation to the information model of development and improvement of the quality of research results in the smart environment. To develop integrative methods of simulation visual dynamic computer modeling of gas microprocess, and on this basis to create a presentation dynamic graphical computer visualization of the distribution of velocities of molecular atoms, ions, electron, and phonon. Gas used the matplotlib module of the Python language to provide a new interpretation and definition of the fundamental concept of molecular physics and thermodynamics. The definition of concept of molecular phenomena, their properties and characteristics were formed on the basis of generation of the works Bernoulli, Gepard, Krenning, Clausius, Mayer, Gauss. It should be noted that scientific used mental and mathematical models. Since the 20th century, the concept of ideas of gas, ideal gas, acquired fundamental importance and has received consideration in the scientific, industrial, and educational field. Justification of mathematical modeling of this concept is considered by Kronberg, Krivadula, Boltzmann, Rusakov, Shakurdova, Golovina, Lushak. According Bykov, Oleinik, Sitnik, Zinovieva, and others, an open educational ICT environment is more productive in assuring accelerated knowledge equilibration, effective in using the accumulated scientific and technologies experience of making more efficient in transferring information from the students to another. However, almost no significant change have been made to definition of molecular concept, the potential of essence of the molecular distribution function by velocities has not been fully used, which does not assure the transition from providing the amount of information accumulation to an information model of development and quality of results, which was successful studied by Bykov, Oleynik, Samoylenko, Betsurovska, Dutsenko, Semerikov. Maxwell research is associated with the study of a number of mathematical models. The course of the study is presented in the diagram. The development of ICT makes it possible to visualization add dynamics to the course of research. Presentation dynamic computer visualization gives a reflection in dynamics. The development integrative methods of visual dynamic computer simulation make it possible to eliminate the drawback and not only build a dynamic model of the distribution of molecules by velocity, but also to trace this distribution in any velocity neighborhood of computer graphs. Accordingly, a distribution table is drawn up indicated by velocity intervals, and for each of them, the probable number of molecules in interval is determined the number of the relative fraction of molecules. We constructed momentum distribution graphs for helium, nitrogen, oxygen, carbon dioxide molecules. The horizontal axis shows the momentum parameters, and we vertical axis show the values of the distribution function. We, for convincing the say on the vertical axis for carbon dioxide and oxygen of different from these nitrogens and helium. The development methodology was tested in the educational process of the Central Ukrainian State University, named after Vladimir Vinnichenko, and the Dnipro State Medical University. The students in this, at the implementation stage, students of the special secondary education, physics and astronomy, secondary education, mathematics, in the Central Ukrainian State University, and students of medical specialists on the State Medical University were involved in the experiment. 6 teachers and 98 students took part in the formative stage of the experiment. 56 the experimental groups and 32 of the control groups. Maxwell distribution modeling programs were integrated into educational process in the disciplines physics, general physics, physics by professional direction, biophysics. When we do this research, our students, Roman Ostrovsky, help us to for our participant in the development and testing our program. Thank you for our attention. Our attention.
Okay, thank you, Natalia. Maybe something want edit, do edit. Okay, or maybe there are some questions. Okay, if you can I ask you, did the modeling activity influence students' procession or randomness, equilibriums, or statistical interpretation in physics?
Can I help our students that which included into this
Yeah.
program?
Good afternoon, dear colleagues, and good afternoon, dear participants. I am Roman Ostrovsky. I am participating in the development and testing program. Of course, I am gonna to answer your question. Students were included, of course, of testing and statistical analysis. We got tests, we got questions for the students, and of course, we got opinion of the students which was participated in this program. And as a result, we got the conclusion that our theory, the newest theory of Maxwell, is gonna to work, of course, because it's the newest one. And in the nowadays, we got, of course, we got some standard theories, but this article was, we got the main target to show you the newest theory of Maxwell. And of course, as we see, the results are the greatest one. And that's all what I wanted to say. Thank you for question.
Okay, thank you for your answer, because Maxwell laws really don't study in the secondary school, but student must know it. Okay, thank you. It's very useful topics, and your work is very useful. Okay, there are any questions? Okay, thank you, dear colleagues. And next report from Maxim Pavlenko and Leah Pavlenko and Lotov and Yevgen Pavlenko, experiments in the development and implementation of the course Python for physics teachers.
Where can be realized the Maxwell demon which sorted molecules.
Yes.
Maxim, we're happy to see you.
Maybe in the next. Good day, colleagues and conference participants. Are you hearing me well? Yes.
Yes.
Okay.
We're here.
Okay.
Are you see?
Yes, we can see full screen first.
Okay.
Right.
I'm Maxim Pavlenko from Berdian State Pedagogical University. Today I present our research on experience in the development and implementation of the course Python for Physics Teachers. Our study explores effective approach to integrate Python programming into physics teacher training. Digital technologies and computing are now essential in science education. Python has become popular in scientific computing due to its simple syntaxes, flexibility, and the useful libraries like NumPy, SciPy, and Matplotlib. This feature make Python valuable for both physics research and teaching. Therefore, physics teachers need training to use Python efficiently, enabling them to teach their subject in a more modern way. Our research addresses the need to prepare future physics teachers to use Python for experiments, including virtual ones, educational projects, and modeling complex physics concepts. Our aim was to develop, implement, and evaluate a Python for physics teachers course that help future teachers gain and necessary skill. Our objectives were to develop effective teaching methods for Python in physics education and so measure student satisfaction and perceived usefulness of the course. Our research reveals several key trends. First, computation and programming are now considered essential skills for physics education. Using this skill helps students better understand complex physics concepts. Python is particularly well studied for physics education. It's beginning friendly, yet powerful enough for advanced work. Studies show Python excels in calculations, data analysis, and creating visual representation that clarify difficult concepts. This feature improved student learning in learning and interests. Research indicates that using Python develops critical thinking and problem-solving skills. Virtual environment and interactive simulation also increase student engagement. Importantly, research shows a clear need to train physics teachers themselves. For modern physics teaching, that including computing, teachers must know how to use Python. Effective training approach include project-based learning and physics-focused modeling tasks. While many researchers agree that Python is valuable in physics education, we identify a gap. We need more studied complete training course for physics teachers and their outcomes. This gap guided our research. Our main goal was to design, implement, and evaluate this specialized course through several steps. First, during course development, we carefully planned the curriculum. We based it on proved teaching methods following current STEM education trends and considered future physics teachers' need. Next, in the implementation phase, we thought Python for physics teachers as an elective course. Students studying to become secondary education teachers in physics and astronomy took this course at Berdyansk State Pedagogical University all the 2 academic years. Finally, in the elevation phase, we assessed student satisfaction and perceived usefulness of the course. We primarily used quantitative methods, applying to a modified version of the course experience questionnaire, supplemented by student comments. Our course consists of 5 ICTS credits, consists of 13 lectures and 12 practical. Structure, of course, you can see on the slide. A central focus was applying Python to solve physics problem at the school level and visualize key concepts effectively. In Module 1, students worked with real data from kinematics experiments. They received CSV files with time and position data for uniformly acceleration motion. Their task was to write Python code to read this data, calculate instantaneous velocity and average acceleration. This connected basic programming skill to fundamental physics concepts and data analysis techniques using file handlings and array operation. In this slide, you can see next template task. Students visualize project motion using Matplotlib. They create programs to plot projectors based on initial velocity and launch angle, and extend task in solved showing multiple projectors in different angles on one graph. Clearly illustration dynamics and ballistics motion concepts. This assignment primarily used Matplotlib and custom Python function. Our study involved 19 university students training to become physics and astronomy teachers. They took our Python for Physics and Teachers course at Berdyansk State Pedagogical University between 2022-2024. To evaluate the course, we used an adapted version of course experience questionnaire. We modified it to fit our specific Python course and gather accurate information about student experience and teaching effectiveness. The question contains 16 questions grouped into 5 main areas. Before full implementation, we validate the questionnaire by carefully studying the original CE creating a well-designed question and testing it with a small group. For data analysis, we checked questionnaire reliability using Cronbach alpha and examined average score. and the relationship between different aspects using Spearman's correlation. First, the good news is that the questionnaire used was reliable. This means we can trust and answer students gave us. And overall, the students gave positive feedback. They generally like the course. If we look at the like most on average, they gave the highest score to how clean the course goal were. They understood what they need to learn and do. They also really like the practical use of the course, saying it was relevant for their future job as teachers. The quality of teaching was also rated well, and the overall happiness with the course was good. This was one area that got slightly low score, the test and assessment. So this is something we might look at improve in the future. We also analyzed the relationship between different aspects of the course experience. We found a significant correlation. Teaching quality strongly connected with students' overall satisfaction, highlighting and crucial importance of effective instruction. Another strong connection existed between the course's practical usefulness and clear goals. When students clearly understood an objective, they found the practical components more effective. This finding emphasizes that quality teaching and relevant practical content are essential factors for course success and student satisfaction. Our study demonstrates that the Python or physics teaching course was highly effective. Students expressed satisfaction, particularly with teaching quality, clear objectives, and practical relevance, aligning with modern science education approach. The application of Python to authentic physics tasks proved successful, helping students connect programming with physics concepts while developing important digital skills. This confirmed finding from previous research. One area for implement is assessment method, which received somewhat lower rating. Overall, the course consists taught Python to future physics teachers in a meaningful and engaging way. In conclusion, our Python for physics teacher course effectively helped students develop essential programming and modeling skills for physics education. Our study had limitation, including a small sample size and single institution focus. We also lack data on how graduates will apply this skill in actual classroom teaching. Future research should follow these students to observe their classroom implementation of Python. We could also expand the course to more students across different institutions and develop better support for programming beginners. This study clearly shows that teaching Python to future physics teachers is both feasible and valuable. These positive results support continuing and refining this course as an important step in modernizing physics teacher education. Thank you for your attention.
Okay, thank you for your reports. Okay, Sergey Alexeyevich, please. You want to ask?
Thank you, Svetlana Leonidovna. Thank you, Maxim Petrovich. I have some provocative questions.
I like it.
Our experience of using Python and Glow scripts almost 20 years ago was associated with some typical problems. 2005, 2007 years, our students already have some are accessed to the internet, and all classical Sherwood presentations from the vpython.org they can use. They can use to make, based on these presentations, their home task, laboratory works, etc. Yes, we used a similar approach, but we have two obstacles. First of all, to make less or more good model, we need for from 18 to 140, 50 lines of code. In a classical form at the lections, it was impossible to write by chalk on the board this Python program. When we try to make some templates for the students, a lot of code are completely delete and physics ideas for our students. It was students at the 5 year of learning. The course of elements of computer modeling, of mathematical modeling, etc. The two problems: a lot of code, a very small part of students really understand this code in fullness and don't understand the physics. Those who understand physics of this model don't understand the full code. Oh, yeah. We eliminated this code part and returned to the directory operation with formula in spreadsheet. For today, your experiment is last 3 years. When I'm trying to solve these problems using any an even outdated large language model, I got a complete code, unique, well commented. All the problems that you propose your students will be fully and with great it seems to be understanding graded by the students. My questions: we cannot eliminate the using of these tools, but we need to develop understanding in our students, both in physics, both in triangulations of physics, modeling, and computer science. How you resolve this bottleneck critical issue when formally you can got any code, any moreover it will be syntax correct code, and we can get no understanding in our students, no development.
We thank you for the question. We start from the very simple program, and this program we make our student made for in the first model of our course, and the second model our students could make could made more complex task, and they understand Python and understand code they write. And we asked our students to understand, to reproduce and explain their code on laboratory work.
Thank you, Maxim Petrovich. I see a real dialogue with my students when he in real time explain all using appropriate large language model, which was hidden from camera, etc. So. Main question: how can we really control this process? How can we evaluate that our learning outcome was developed through our instruction? I think it's more problems than than answer.
The solution.
Thank you for your question. A big language model make many problems for teachers and lecturers. And now I try to explain my students and code and make some changes in code, and when students make these changes or not didn't can make these changes, I understand online changes without offline on today's online changes. If student answer and rewrite code.
No, classically, we need to communicate with our students to indicate. But I remember one more classical way to enter this bottleneck. When in the France at the beginning of the 18th century, Lupin, I'm sorry, was a former chief, was invited as a head of Paris police. So instead of a set of tasks that that should eliminate and involve of large language model, probably it will be more productive. It's really actively used and involved in our instruction. That our students should use this model and explain, modify, and product a new model. I remember the old, no, I'm sorry, in Russian. In Ukrainian. Якщо пиятику не можна, если пьянку нельзя предотвратить, ее необходимо организовать и возглавить.
Да.
No, probably it will be a kind of new approach that will be help us to enter this bottleneck.
We try to заучить our students to use large language model as tutor for learning programming, learning physics, or in different way. ChatGPT as a teacher.
As a teacher, as an agent, as an fine-tuned, specialized bot,
trainer.
when we again return to the papered ideas, we need to teach this program, we need to teach this computer to understand themselves. Oh, I'm sorry for the discussion. Thank you.
Yes,
Thank you very
but,
much.
Thank you.
but it's
Thank
a
you.
problem
Very,
of
very useful.
all of us because we have some problem in the physics, in the astronomy, and in the programming. And we can use ChatGPT and such program for using students, yes. And maybe when a student teach other student or other people, they learning themselves. Okay, thank you for discussion. It's very interesting listening to you. Okay, maybe there are also question.
No question, and we have a last report for today, and this report by Svetlana Malchenko has title Implementation of a competence-based approach in teaching astrophysics and astronomy. Svetlana, please.
Okay. I hope you're not tired. I try to short and quickly do my report about astronomy and astrophysics in the secondary and high school because astronomy is very interesting but not very popular. Interesting for students, but not popular among the teachers of physics and other classes. But for my opinion, astronomy is a very, very useful subject and very useful lesson because we can development many competence, but and not but. And it is main of task in our school program in the national school. So implementation of competency-based approach the teaching physics and astronomy. And okay. As I say, astronomy is fascinating field in that natural specs. Seriously, it also often acquire opportunity to develop a wide range of essential skills. My research focused on implementation competency-based approach. This approach shifts the emphasis from simply memorizing fact to acquiring and applying practical skills. In this presentation, I will discuss the key elements of approach and share some practical examples of how it can be applied. Today's world depends more than just theoretical knowledge. Students need to be able to adapt, solve problems, and work effectively in teams. A competence-based approach directly addresses this need by focusing on developing skills that are relevant to both professional and personal life. Think about it. Astronomy involves not just understanding complex concepts, but also analyzing data, using technology, and communicating scientific ideas. This approach helps students develop a scientific worldviews and the ability to learn independently. a critical skills for lifelong learning. On the what are core principles in this approach? Firstly, result-oriented, integrating knowledge, skills, and abilities, relevant and realistic, practical and activity, flexibly and adaptable, interdisciplinary, reflection and self-assessment, competition and communication, and other many principle of competency and some key competency in astronomy, some specific competency in astronomy. Natural science competence, understanding the law of nature through studying celestial phenomena or universe phenomena. Mathematical competence, applying math to calculate orbits, distance, and other astronomical parameters, distance, or physical parameters of body of in the universe. Digital competence, using software and database to model and analyze astronomical data. Analyze competence, developing critical thinking and evaluation information, and forming evidence-based arguments. Research competence, conducting investigation and driving scientists, concluding their project work, work in the group, in the teams, and etc. Communicative competence, effectivity sharing, finding, and participating in the scientific discussion or discussion about our universe, about our place in the world, about our future. Environment and literacy, understanding the impact of space exploration and relative ICs. Creative and innovation, designing original research project and developing new approach. Ethical competence, considering the moral implication of space exploration and the use of space research. And of course, developing specific skills like observing celestial body, analyzing astronomical data, astronomical information, spatial thinking. There are many special skills which we can also develop in the class of astronomy, such as on the slide. So, if you use competence-based classroom, we need to use and change learning and should be simply testing knowledge. It should measure development of this key competence. This evolving combination of formative and summative assessment. On the slide, you can see some principal formative assessment method because it was more important in the competency-based learning. Okay. In the paper, you can find some example of laboratory work from the astronomy, which can do with different digital tools without specific astronomical equipment because not each school has a telescope or some specific equipments for telescope or other equipment. Okay, next. Okay, in the work we can find in the paper we can find some example of lessons and one of lesson is study of the apparent motion celestial body. Main task of such a lesson is equipping students with a permanent motion to celestial body to develop skills in their work with astronomical simulator, to form ability to analyze observing and draw conclusion. And there are some results which was very useful for not for only astronomical, also for physics and astro for understanding of universe and also for understanding scientific nature of the world. And my students don't thinking about the Earth or is Earth or sphere or is not sphere. So not we make action in the paper for the laboratory and practicals work because when we study such a lesson, when we not study, when we use such a lesson, such class, people and student can involve it in process of educational as in discussion of problem and such study, such work is useful, is helpful. So we proposed some laboratory works when pupil and student can do in the offline and online educational. And conclusion, the competency-based approach offers a powerful framework for teaching astronomy in a way that is engaging, relevant, and effective. It empowers students to become active learning, critical thinking, and skills problem solvers. By embracing the approach, we can inspire a new generation of astronomers and equip all students with valuable skills for success in 21st century. So, thank you for your time, and I pleasure to answer your question.
I have a small question.
Okay.
Could you share more details about developing ethical competence in your course?
Yes, because ethical is very interesting question in the with the students. On the my experience, we discuss it on the class methodical of astronomical educational because it's very important. So as we do it, first, I am sorry, universe pollution, or not universe, space pollution, забруднення космічне. Space pollution, the first. Secondary, the development in the different country, which today is rocket development, and it not use this space on the scientific, yes. They use in the other many problems, and it isn't astronomical, yes, because astronomy is a very, very good scientific and quiet. So, also in these terms, we use it, we speaking about astrology, but not a bit.
Professor Semeriko has a question.
Thank you. Svetlana Leonidovna, today we have a lot of issue to the access of the classical astronomy equipment, despite that you can use a quite modern telescope, etc. What about the real distant access to equipment for the students is first question. And second question, what about using data that producing by you in your research, observation, etc., and producing by other laboratories? How can our students be involved to process this almost on-processes data to make their own research and own discoveries?
Okay, thank you for your questions. For the first question, it's very hard to organization real observing with telescope. With a telescope, we have many telescope, but I need good weather. I need many interesting bodies on the night sky, and I don't use such a lesson without moon. When moon is first, we organized some class in when moon in the first phases, because in another we can't see moon, and the student, if you come first in the first time, you haven't very interesting emotion.
But what about amateurs observation without special equipment from the student side?
Yes, we only amount, because in the professional they must be some astronomical provisional knowledge, and they can use mathematics apparat or programming, computer science, because they in the professional astronomical it's very difficult. But you have a second question about what we used the professional date. Yes, of course. All of our students used the date of the solar observation. It's very easy. Solar activity. It's a first. Secondary is binary stars. They can understand it. They can't change needing diet, they can analyze it. So not only double stars, also we used maybe other interesting bodies. We used Simbad, used Wizard, many, no, not many, Simbad and Wizards catalogs, and not my student, by a student from our school, Kryvyi Rih school. One of people 3 years ago, they discover a new type of stars. She was in the night classes. They only analyze it such catalogs. As I remember, it was Simbad. But she used computer science, specific computer apps.
Thank you very much, Svetlana. Very impressive. Thank you. Thank you.
Okay, I hope when now our curriculum, our program, we study astronomy from the fourth course, and next year I was study with this student astronomy in the master's course, and maybe on the astrophysics we start do scientific works, really scientific works.
No. Svetlana Leonidovna was 4 years research in our Kryvyi astronomical laboratory. And
Yes.
do her PhD in this laboratory on the
Okay.
equipment.
Thank you. Yes.
Thank you,
Yes,
Svetlana, for
because
your...
yes, unfortunately we can't use this laboratory today, and more than 10 years ago. Okay, thank you.
Thank you,
Maybe
Svetlana, for your very impressive report and answer for question. And this is our last report. And I see that all of participants turn on your camera.
Yes. Yes.
Thank you.
Thank you. You all of here.
Thank you for your report, for your presentation, for your attention, and we hope we will see you next year, and we will see you in our next section conference example tomorrow.
Yes, tomorrow geography and scientific
Geography
affairs.
and chemistry. We have.
Geography and chemistry. Okay.
Yes,
Sorry.
and tomorrow we have STEM section and chemistry. And on the Friday starts section computer science education, augmented reality and education, computer technology education, and Saturday educational technology education.
Okay.
Thank you very much for the hospitality, and hopefully we will meet again. Thank you.
Thank you, George. Yeah, okay. And I hope that our work from the physics educational was продовжиться, да? Was in the next year.
We
In the next,
will continue. We definitely
yes,
will
will continue,
to
and we have students, and we have new students which was which will take part in our conference and in our university.
We have a spirit, we have inspired, and we have a desire to continue this, not work, to continue this journey. Thank you very much for all for to make an exciting session of our conference. It will be it was as for me the best session as for today.
Thank you.
Thank you. Thank you. Bye.
Thank you.
Bye.
See
Have
you
a good afternoon.
next time.
Bye.
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 Goodbye. Goodbye.